Alright, we're going to look at what happens when the value of the load resistor is outside the specified range on the low end. Okay, so actually this is a mistake here. This should be what happens when the load resistance is less than RL minimum. Okay, because this here, the 50 ohms in this example, that's RL minimum. Okay, and then the largest resistance in the range, that's RL maximum. Okay, in the next video we'll look at what occurs when RL is greater than RL maximum, but right now we want to see what happens when the load resistance is less than this minimum resistance in the specified range. So this is the same example as the previous video, 24 volt voltage source, 50 ohm resistor. Here's our Zener diode in parallel with the load, and the Zener voltage is 12 volts. Well, the easiest way to answer this question is to just choose a value of RL just below this RL minimum. So I chose RL to be 49 ohms. And now we're going to go ahead and do the analysis to see what the state of the Zener diode is. Remember, in order to have voltage regulation, the Zener diode's got to be conducting in the reverse bias direction, acting like a voltage source of VZ, because that's what maintains the load voltage at a constant amount, right? That constant amount being VZ. Well, just like in the previous video, to find the state of the Zener diode, the easiest thing to do here, since we need to get VD across this open, okay, and that's the same voltage as what's across RL, is just to go ahead and use voltage divider. So, VD, oh, I forgot to put the ground here in the circuit. Right, VD, like we said, is VA minus VK. VA is grounded. Okay, so we just got to find VK, which is the same voltage as what's across RL. So VK using voltage divider is just going to be 24 times 49 over 99. Right, 99 being 50 plus 49. And if you work this out, it comes out to 11.88 volts. Okay, which now if you plug in here, you get a VD, a diode voltage of minus, it's an equal sign, minus 11.88 volts. So now we take this value and we go back to our ideal Zener model, which is a few pages back, right here. So you see what occurs when RL is less than the minimum value in the specified range is that the Zener diode does not conduct. See right here, VD minus 11.88 would put us in this second row here, where the Zener diode is truly acting like an open. Okay, so our assumption, so went one page too far, our assumption of reverse bias open in this case is true. So you see, that's the issue when RL is less than the minimum resistance in the range, is that you no longer have voltage regulation. Okay, so you see the answer to the question here is, if we come down here, is no voltage regulation. Okay, that's what occurs when you're outside the range on the minimum end. Alright, now if you want to find what RL minimum is for a particular circuit like this, well, there's two ways that you can come up with what the RL minimum is. So here's a different circuit. We have an 18 volt source, 1 k ohm resistor, and then our VZ in this example is 10 volts. So now we have a 10 volt Zener. Well, one way to find what that RL minimum is to treat the Zener diode as an open. Okay, so you're treating the diode, Zener diode, as not conducting, and then you're going to set VRL equal to VZ, and then just solve for RL using voltage divider. Okay, so you see your equation's going to look like this, where VRL is equal to 10 VZ, and then that's equal to the source voltage times ratio of resistances in our voltage divider equation, which RL is in the top, right? And RL plus this 1K ohm resistor is in the denominator. So when you set up this equation for VRL equal to VZ, when you solve for RL, this will be RL minimum. Okay, and if you go ahead with these values and you solve for that resistance, you should come up with a value of 1.25 K ohms. Okay, now another way to get RL minimum, okay, this is a different circuit that you can analyze to get the same answer, is that in this circuit you treat the Zener as a voltage source of value VZ. However, the current is 0 for the Zener, okay, because this represents the case. Remember, when you're on the minimum end of that specified range where RL minimum is, that's the very cusp of when the Zener diode is going to conduct. So you see here we're representing the Zener as a 10 volt source, but we're saying that current is just at the point of being non-zero, but we're going to treat it 0 to do the analysis. Just like up here with the open, the current is 0 for the Zener, and then we just set VRL equal to VZ. Well, here, you know, we're doing it more explicitly, showing the Zener equal to a voltage source, which is also going to make VRL equal to 10 volts VZ, just like it is up here. But we're saying that that source has 0 current, just like the open has 0 current. Okay, so it's just a slightly different way of representing the circuit, but again, you end up with the same answer, because here RL, okay, RL minimum, okay, using Ohm's law is just going to be the voltage across RL, which is 10 volts, since the Zener is acting like a 10 volt source and they're in parallel, and then divided by the current, which, since there's 0 current through the 10 volt source that represents the Zener, the current's just going to be, the current through RL is just going to be the same current as through this 1K, right? Because since there's no current going through this path, all the current for the 18 volt source travels this path here that contains the 1K and RL. So this would just be the voltage on one side of the 1K minus the voltage on the other side of the 1K, right? That's our voltage difference across the 1K divided by 1K. So you see this is going to be 18 minus 10 over 1K. Alright? So you see you're going to have 10 volts divided by 8 milliamps. Okay, which is also 1.25 K ohms. Alright, so either analysis gives you the same answer. You know, personally, I like this representation, this circuit representation to solve for RL minimum, just because representing the Zener diode as an open, it should be very clear there's no current here, and you know, with a series circuit like this, we can just use voltage division. Again, this works. The reason I don't particularly like this particular circuit to analyze is that often students will make the mistake that if they show the Zener as a voltage source, they think this, or they make this current something other than 0, which of course is going to throw off your calculation. So you know, it's just personal preference which circuit to use, because they both work, but in either case you just got to be careful.